Okay, what I'm going to do here is just kind of walk through the homework assignment and try and guide you through what's going on. Let's start off with the first problem. It says, if f of x is defined to be x squared minus 4x over x minus 4, and g of x is equal to just x, is it true that f equals g? Well, let's take a look at this. Let me change my color here. Let's look at that numerator up here. X squared minus 4x over x minus 4. We can factor an x out on top and be left with x minus 4 and then over x minus 4. And now what we're allowed to do is we're allowed to cancel this factor. Now, when we do that, we have to be careful to tell ourselves that's okay to cancel as long as x is never 4. If x is 4, then we get 0 over 0 there, right? This would be 0, this would be 0, and therefore you have division by 0 to be undefined. So what we're saying is this. This up here will turn into x as long as x is not 4. Okay, so we can make that cancellation as long as we guarantee x is not 4. So this function f here is really equivalent to just x. So it's equivalent to g as long as x is not 4. So let's just try real quick and figure out what f of 4 is and what g of 4 is. Well, if we plug in 4 into g, let's start with g. Well, g is just the identity, so you plug in 4, it spits out 4. But with f, we would get, let's say, top left corner is 16 minus 4 times 4 is 16 over 4 minus 4, which is 0. We get 0 divided by 0. This is undefined. So these functions are not equivalent. They are not equal to each other because at 4, one of them is undefined, the other one is 4. Anywhere else other than 4, we would get the same values. So if you try and plug anything else in, f of, let's say, 5, and you compare that to g of 5, and g of 5 is 5. If we plug 5 into f up here, we get 5 squared is 25, minus 4 times 5 is 20, over 5 minus 4 is 1, so you get 5 over 1, which is 5, and those two match. So the g and the f function are identical to each other except one place at 4. At 4, one of them is actually defined, the other one is not defined. So we cannot say that those two functions are identical everywhere. All right, I hope that makes sense. All right, let's move on to the next problem here. All right, the graph of the function is given here. So we've got this graph. Make sure you pay attention here that the origin is that point right there. Okay, that's 0, 0. You go out to the right 1, 2, 3, 4. Here, 0, you go up 1, 2, 3, 4. So it says state the value of f of 1. So what I do is I go out to 1, and I look up on the function to figure out what the value is. So at x equals 1, I go up 1, 2, 3. So the value here is 3. All right, estimate the value at -1. So here I go -1, and then I go to the function. It looks like it's gone down maybe, I don't know, 0.2, 0.25. So something like -0.2. And it's a negative number, right, because it's below the x-axis. For what values of x, okay, what values of x is the function equal to 1? So if I go up to 1 on the y-axis, and I look at where my graph hits 1, it would be at these 2 points. The corresponding x values, let's see, this is 2, would be 3, right? At 3, we're up here at 1, and then, of course, at 0. So x equals 0, and at x equals 3, we would get that. We would get 1 to come out. All right, let me clear that out. Switch this over. Let me see if I can move that down. Estimate the value of x such that the function's value is 0. So what I want to do is go to the function. I want to know what x value gives me 0. So here's y equals 0. Y equals 0 right there. Where does that hit the function? And that looks like it happens here. And that looks like it's at about -0.75, something like that. So I'd say -0.75. And it's estimating, right? So we're just looking, these two problems, we were just kind of looking to try and get the best value we could find. All right. Next question. State the domain and range. Enter your answer using interval notation. So let's talk about domain here. The domain is all the x values where your function is defined. So notice that my function starts out, if I look at my x values, for this x value, I have something. And for every x value, I have something all the way until I get to the end. And at the end here, I have, that's my value that my function ends at. So that looks like, let's see, -2 is where it starts, and it ends at 1, 2, 3, 4. So it looks like for domain, we're looking at the interval from -2 to 4. Actually, we can close that interval, assuming that the endpoints exist. Okay, so x is an element of that interval. Then, for the range, we're looking up and down on the y-axis. So let me switch my color up here. The y-axis, let's see, the highest point I get is up here, and the lowest point is down here, and it looks like everything in between there. So that looks like -1 all the way up to 1, 2, 3. So my y values are an element of the interval -1 to 3. And that's it. Okay, let me clear that out. All right, so what is, on what interval is the function increasing? All right, and the answer in interval notation. So increasing means as you move from left to right, we're going up. So it looks like to me that starting at this point, as I move to the right, I'm going up, 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 all the way till I get here, and then I start going down. So what we want to know are the x values where that happens. So it's between here and here. On my x-axis, I want to know what values I have. So again, starting at 0, -1, -2 here, all the way to here, which is 1. So it looks like f is increasing when x is an element of the interval -2 to 1. And on increasing, decreasing, it's okay to put it in open interval. Either way will work. You just have to be a little careful sometimes on the closed intervals for, whether or not your function exists at that point or not. So, okay, let's come back there and clear that out. Okay, here we go. The graphs of f and g are given. All right, here they are. It says state the values of f of 2 and g of 3. So I'm just going to be looking at this function. I'm going to be going to, let's look at my f function, which is this reddish one. And I want to go out to 2 on the x-axis, 1, 2, and go find the function. It looks like the value of the function up here is 2. And now I want to go to g of 3. So g is the blue function, right? G is the blue one. I want to go out to 3, and I want to go up and see what its value is. And it looks like it's almost 1. I'm going to say it's like 0.8 or 0.9. 0.9, let's say. Curious to see what they have here. Yeah, well, we won't look at it, but bring that back in there. There you go. Okay, next part. For what values of x is f and g equal? So we basically want to know what x values, at what x values do our functions intersect each other, and that would be at this point and at this point. And we want to know the x values. So it happens at 2, and then over here 1, 2. It looks like -2 is where that one hits. So we would say when x is 2 and -2. Okay, next part, C. Estimate the solutions to the equation f of x equals -1. So let me clear everything out. What they want to know is where is our function f -1? So starting again at my origin. Let's see if we, why am I not? Let's see, lost my pen here. Oh, there we go. Here's the origin. All right, there's my origin. I want to know when my function's value is -1. Here's -1. I want to know when my graph hits that. Okay, that's going to be here and here. So what x values would give me that? It looks like I have two of them. Looks like at, oh, I went too high. Here and here. So looks like 1, 2, 3, 4 at 4. And then also here at -1, -2, -3. So 4, -3 would work there. Okay, next one. Let me scroll down here. Where's the function decreasing? Okay, decreasing. So, oh wait, which function? F. So when is the function f decreasing? So f would be decreasing whenever it's going down. It looks like right here at this top point, from there to the right, it goes down, right? It's going down here. So my x value here is 0, and then it goes all the way till I get to this x value, which appears to be 4. So from 0 to 4, it's decreasing. All right, clear that out. State the domain and range of f, state the domain and range of g. So I'll do these both together. Okay, f, let's talk about the domain. Starting, here's our origin. Let's see, f looks like it starts here and ends here. So 1, 2, 3, 4, from -4 to 1, 2, 3, 4, +4. So for f, the domain goes from -4 to 4. The range is up and down. So it looks like from here all the way up to here. So from -2 to +3. Those are our y values. For g, looks like g starts out same place here. That was -4, but g stops at 1, 2. It looks like it stops at 3 up there, right? So for g, the domain was -4 to 3, and the range for g, well, this one's kind of tough. Looks like it's just right here. Maybe at 0.5 is the lowest it ever gets, and the highest it ever gets is up here, and that looks like 3, 4 up there. So maybe we say something like from 0.5 or 1/2 up to 4. Okay, I hope that makes sense. Clear that out, and let's proceed. Got all that, domain, range. All right, a spherical balloon with radius r inches has a volume given. Find the expression that represents the amount of air required to inflate the balloon from a radius of r inches to a radius of r plus 4 inches. So we're just going to look at the answer here. It's a little easier. Whoa. I hope I didn't lose my... Okay, a spherical balloon with radius r plus 1 has volume of v of r, I said r plus 1, r plus 4, has volume v of r plus 4. So if we plug r plus 4 in, instead of r, we have r plus 4, and we expand this out, that means we multiply that all out, we get this, and we have the 4/3 pi in front. We wish to find the volume of air needed to inflate the balloon from a radius of r to r plus 4. So we need to find the difference. So we're trying to subtract this volume, the volume at radius r, subtract that from the volume at radius r plus 4. So we take what we just got, everything up here, and we subtract from it the volume at r, which is this, and we get this. So we have a new formula that basically tells us the amount of air we would need to get this radius to go from r to r plus 4. So picture-wise, here's what we've got. We've got a sphere. It's got radius r on it, and we want to blow that thing up. See, r is not given, but we want to blow that up to a bigger sphere like this, and that radius we want to be r plus 4. How much air would we need to do that? This is how much air we would need. That's the volume of that air. It's the difference. It's the volume of air in between these. Okay. Hope that makes sense. Clear this out. Switch it back. Close that. Get back to my assignment. Okay, evaluate the difference quotient here. So I think this is going to take a little bit of work. Let me do this first. Bring this new thing in here. Let me just add page. All right. I need to be able to get the, I want to move this. Let me move it. Just let me make it smaller. I think that's enough to get it in there, though. Okay, so what we have here is f of x equals 2 plus 4x minus x squared. We want to find f of 3 plus h minus f of 3 all over h. So what I'm going to do first is get this top left corner. Let me blow this up. Oh, no. I wanted that. Okay, so top left corner is what we get when we plug 3 plus h into this function for our x's. So f of 3 plus h would be 2 plus 4 times 3 plus h minus, replace that x, 3 plus h, and then squared. We now need f of 3. So what would f of 3 be? We get, let's say, 2 plus 4 times 3 minus 3 squared. Let's figure that out. That's 2, let's see, 12, 14, and then take away 9, we get 5. And then up here, let me go ahead and multiply this out. This is 2 plus, distribute the 4 through, 12 plus 4h. And then I need to multiply this out together, so expand that. And then subtract it. So subtract, when I multiply those, I should get 9 plus 6h plus h squared. And now distribute that negative. Let's go 14 plus 4h minus 9 plus 6h, not plus, minus 6h, distribute the negative, minus h squared. Careful with that negative, needs to go through here. And let's see, 14 minus 9 is 5, and then we get, let's see, plus, no, let's go minus 2h minus h squared. Okay, so that's the top left, and then we have the top right is 5, and we want it all over h. So let's go ahead and write out what this answer is. It's the 5 minus 2h minus h squared, but then I want to subtract f of 3, so I want to subtract 5 and divide all of that by h. The 5's cancel. In the numerator, notice we have h's in both terms, and we have an h on the bottom. So we can factor an h out. Negative 2 minus h is left, and then over h, and we can cancel these h's. So we get negative 2 minus h, and that's it. All right. Let's check out their solution here. Here we go. Same thing. They don't show as much work, but it's there. All right. Next one. So f of x equals negative x cubed, and we want to find this. So that does not look that great. So I'm going to start a new page here. Let's see, we have f of x equals negative x cubed. I want to find f of a plus h minus f of a all over h. So I'm going to try and do this one a little bit faster. Okay, this is going to be equal to f of a plus h. Well, that's what I get when I replace that x with a plus h. So I'll go negative, here comes my a plus h, and I'm cubing it, minus f of a, but f of a, be careful, we have a negative right here. F of a is going to be negative a cubed. Then all of this over h. All right, so now what I'd like to do is I'd like to go ahead and figure out what a plus h cubed is. You could do that on the side, but that's a cubed plus 3a squared h plus 3a h squared plus h cubed. That's what you would get if you multiply that out 3 times. And then we have a negative in front of it, right? So we have a negative in front of all that, and then we're going to distribute that through and change all the signs. So my next line will read negative a cubed minus 3a squared h minus 3ah squared minus h cubed. But then we also have minus minus here, so it'll become plus a cubed, all of this over h. Notice that the a cubes cancel, and then everything else we have has an h in it, so I factor an h out. It's kind of the theme here. We want to get that h on the bottom to cancel. So I just factored an h out of every term on top. Now they cancel. So my final result is negative 3a squared minus 3ah minus h squared. All right, let's look at the next one. Same sort of thing. I want to find now this difference quotient. So f of x minus f of a over x minus a, and I'm doing that for this function. So let's work on that. Here f of x equals 1 over x. And then I want to find f of x minus f of a over x minus a. All right, again, let's work kind of quick here. This is equal to, what is f of x? Well, it's 1 over x. Minus, what's f of a? Well, that's just replacing the x in the function with a, and then divide all that by x minus a. Now what I'll do, since I see that I have a fraction and a fraction over something, so it's a complex fraction, I get a common denominator on the top. So that means I'll multiply the top and bottom here by a, and I'll multiply the top and bottom here by x. When I do that, I get a over ax minus x over, let's write it as ax, all over x minus a. Now I can combine the numerators together because I have the same denominator. And notice that these two, oh, not what I wanted. Notice that these two, and this is like a fraction down here over 1, that those two are off by a sign. So they're almost the same. So what I'm going to do is on the top, I'll just factor a negative out. That'll turn into negative a plus x, which is the same as x minus a, over ax, over x minus a over 1. And then remember, when you have a fraction over a fraction, this one here flips up here like this. So division is the same as multiplication of the reciprocal. And then when we do that, we notice that the x minus a here and the x, this is an x minus a also cancels, but I still have a negative right there. So my result is the negative and then the 1 on top, so negative 1 over the denominator. The only thing left is ax. That's it. All right, find the domain of this function. So when we look at this function here, I think I can do this one without a separate page. The domain is basically everything that makes this function defined. So I just need to know when this denominator could possibly be 0. So x squared minus 49 equals 0. That means x squared must equal 49. And when I take the square root on both sides, I have to do plus or minus. Square root of 49 is 7. So plus or minus 7 is when I get 0. So the domain of this is everything except 7 and everything except negative 7, which can be written like this, or it can be written like this. So all real numbers such that x is not 7, or not negative 7 and not 7, or everything from negative infinity to negative 7 not including -7, unioned with everything from -7, not including -7, all the way up to 7, not including 7, union everything after 7, not including 7, all the way to infinity. See, clear that. Okay, next one. Find the domain of this one. So same sort of thing for this domain. I just need to make sure that the x squared minus 9x, that thing has to actually be greater than or equal to 0, because it can't be negative because it's under a fourth root. And it can't be 0 because you'll have division by 0. So the way I do this is, the way that I'm going to do this is I'm going to rewrite this as an equation, factor an x out, and then I'm going to get two solutions, 0 and 9. So what I know is this. If I go to 0 and I go to 9, this equation is true, which means that it gives me 0, which means that, or this is 0, which means I get division by 0, which is undefined. So I know that my function cannot be defined at 0 and 9. Question is, what's happening here, here, and here? So I'll just think about this. This by itself is a parabola, right? It opens up, and these are the x-intercepts. So I know that that parabola looks something like that. That's what x squared minus 9x looks like. And I would like to know when that is positive, which means when is it above the x-axis. And that would happen over here and over here, but not in here. Here I'd be below the x-axis, so I'd be negative, and I don't want that. So what I can say is that everywhere from negative infinity all the way up to 0, but not including 0, this thing is greater than 0, and therefore it's defined. You know what? I just realized, stupid me. This, I don't want equal. I want greater, strictly greater. I said it, but I wrote it down incorrectly here. I want this thing underneath the radical to always be bigger than 0. Okay, it's got to be positive, or else I can't take the fourth root of it, and it can't be 0 because I'll have division by 0. So I don't want to include these points, is what I'm getting at. So negative infinity, 0, do not include it, and then union with everything past 9 forever. Okay, moving on. Find the domain and range of this function. So again, what's under here has to be bigger than 0. And it can be 0 because we don't have division here. So we need to make sure that the 81 minus x squared is always greater than or equal to 0. Well, you could solve this real quick. Set this, turn it into an equation first. Solve that, you get x is plus or minus 9. So I know that when I'm at 9 or negative 9, I get 0, which is okay. So these points can be there. And the question is, what's happening, in these three regions? Well, again, this right here, if we look at it by itself, is a parabola that opens down. So I know it looks like this. And therefore, I want to know when it's bigger than 0, which is going to be right in this area right here. But not over here, not over here. There, our graph would be negative, so we don't want that. So we want everything between negative 9 and 9, including negative 9 and 9. So our answer here, this is our correct answer, picture-wise. But as far as the domain is everything between negative 9 and 9. The range would be the highest it would ever get. Well, the highest this will ever get is when this under here is as big as it can be. And since you're always subtracting a number that's positive, the greatest that 81 minus x squared could ever be would be 81 by itself. And the square root of 81 is 9. So the highest point it could ever get is 9. So the domain is from negative 9 to 9. The range is from 0, because the smallest this could ever be would be 0, all the way up to 9. Bring that back in there, clear that out. Find the domain of this function. Okay, domain of this is everything except 8, because you'll get division by 8. You'll get division by 0. And then to graph this is a rational function that I better go through this. If I factor out the numerator, I can look at it as a difference of squares. over the denominator. And since these factors cancel, that means I have a hole in my graph. I have a hole at t equals 8, all right? Because my graph is undefined at 8. We already said that. The domain is everything except 8. But everywhere else, it just looks like this, which is just a line. It's actually a line. That's like an x plus 8. So it has 1, 2, 3, 4, 5, 6, 7, 8 is a y-intercept and has a slope of 1. So it should look like that, but it has a hole at 8. So if I go out to 8 here, I should have a hole in the graph, and then it should continue out. So let's see which one of these. Here we go. Y-intercept at 8, hole at 8, and it looks like a line. So that's it right there, this one. Find the domain. Okay, domain of this one. Domain, we just need to make sure x minus 7 is greater than or equal to 0. So x must be greater or equal to 7. That's it, just move the negative 7 over. So x must be greater or equal to 7. And then it's a square root function. Square root functions, the only thing that could ever come out of here has to be positive, or it could be 0. So definitely can't be that one. This one looks pretty good. Starts at 7, keeps going, looks like a root function. This one it can't be. And then this one it can't be because it starts at 0. Okay, our domain was from 7 on, so this is the one. All right, let's see. Find the domain of this. Well, we're taking the absolute value of something. You can always take the absolute value of a number. So there's nothing that's going to cause division by 0 or like a square root of a negative number or something like that. So the domain of this is everything. So the picture should exist all, from negative infinity to infinity. So that's what we'd say here. And then this is just an absolute value function. So one way to figure out what it looks like is to clear this. One way to figure out what this looks like is just figure out where it's 0 first. So when is the absolute value of 3x plus 1 equal to 0? Well, that's going to happen when 3x plus 1 equals 0. And that means 3x must be negative 1. And that means that x must be negative 1/3. So if you plug in negative 1/3 right here, you get 0. So I should have an x-intercept at negative 1/3. So it's not this one, looking like that one. Not this one, not that one. So this is it right here. You could get it by testing some other points too. All right, find the domain of this function. So first, what I'd like for you to see on this, where did my cursor go? Uh-oh. There we go. Lost my cursor there. Domain of this, I can plug any value I want of x into here because it's a linear function. Here it's a linear function. So these are both defined everywhere. But I need to make sure my function is defined where these two piecewise, this piecewise function comes together. So at 2 is where they switch from one to the next, and at 2 I am defined. See that little equal sign there. So this is a well-defined function. It should exist everywhere. It's going to have some possible jump in it, but I am defined everywhere. So my domain would be all real numbers. Now, as far as the graph, what I need to do, one way to approach this, start out with your graph right here. 2 is where things are happening, all right? So I'm just going to let's put like this little imaginary line here. Okay, 2 is where this thing switches. So it's doing something on the left, and then it switches and becomes something. To the left of 2, it's something, and to the right of 2, it's something else. All right, let's start with to the left side. So to the left of 2 means x is less than or equal to 2, and this is what it looks like. It has a y-intercept of 2, and it has a slope of negative 1/2, which means down 1 over 2, and then it's a line, so it looks like that. And also, it is defined when we're equal to 2. We plug 2 in here. We get 2 minus 2 over 2 is 1, so 2 minus 1 is 1. So we're here, so solid dot there. And then let's look at what's happening on the other side of 2. on the other side of 2, we are this, right? And that is aligned with the y-intercept of -7, which is way down here. And then it has a slope of 7, so up 7 over 1. Now this isn't part of my graph, and then up 7 again over 1. And now my graph, I can draw it over here, but it's, imagine like a line. Wow, I kind of ran out of room there, but we have a line that's coming up. It's coming through here, but we're not really allowed to draw it until we get to the other side of this line. So somewhere up here, now open circle, and now it goes forever, like that. So one way you could figure out where this is just plug 2 in here, even though you're not supposed to. Plug 2 in. 2 times 7 is 14, minus 7 is 7. So it's up here at 7 is where that hole is, and then from there up, well, that's got a steeper slope of 7. So let's try and look at our options here. No way. Here we go. This one looks pretty good. Well, no, because we have to have a hole there. So look at this one. Looks like it hits at 2, has a slope of -1/2, down 1 over 2. It's got a dot. This one we go up, let's see, to 7, and that's where we have our hole. Now it looks like a slope of 7, up 7 over 1. That looks like that right there. These obviously are not even close. Okay, getting there. Find the domain of the function. Again, this one's defined everywhere because this is linear, this is quadratic, and then where they touch, there's at least one of these has got an equal sign, so we're good. And so let me see if that method kind of made sense. I can do that again here. Oh, wow. Bring that back. Okay. Okay, at 2, we have this switch happening. To the left of 2, right, to the left of 2, I'm a line, y-intercept of 2, slope of 1. So up 1 over 1, up 1 over 1 again. And I am defined there, so I'm going to put a solid dot there. Looks like that. To the right of 2, I'm a parabola, x squared. So that means it should look like this. Remember, you're not allowed to draw it here, but it should go like this. And then at 2, I should be at 1, 2, 3, 4. I should be at that point. And then now that would be an open circle, and then it continues up as a parabola like that. So it's curved. Notice that they meet together, which means that this red one fills in the hole, even though the blue one doesn't have anything there. The red one fills it in. So this is like a line, and then it continues into a parabola without any issues. Compare that to this one. It was a line, and then boom, we had to jump to a hole and then go. So a little different on those. All right, so which one of these is it? It's not this one. Might be that one. No, that one has a hole. Can't have a hole. This one, the parabola's on the wrong side. So this looks like it. Line comes up, and then my parabola out the right side. Okay, getting close to the end here. Well, not quite. Still got quite a bit more here. Okay, find a formula for the described function. A rectangle has a perimeter of 8 meters. Express the area of the rectangle as a function of the length of one of its sides. Okay, so let me try and make this make sense. You'll be doing this later on in the semester. That's why we're doing it now, just to get you thinking. Okay, we have a rectangle. Rectangle, right? It has a length and it has a width. We don't know what that is necessarily right now, but we do know the perimeter is 8. But the perimeter is equal to twice your length plus twice your width, right? So it says express the area of the rectangle as a function of L. So what we want is our area. You need to be able to determine the area by someone just giving you the length. Well, we know the area of a rectangle is length times width. Length times width. Right now, in order to know what the area is, I need a length and I need a width. However, using this equation up here, I can solve this equation for W by moving the 2L to the other side, getting P minus 2L equals 2W. and then dividing both sides by 2, getting 1/2 P minus L equals W. So I know what W is in terms of L, and I can take that answer and I can plug it in right here. So I know that the area is length times W, but W is 1/2 P, but what was P? P they told us was 8, wasn't it? So let me fix that. If P is 8, then half of 8 is going to be 4. So I have a 4 there minus L, which means that if I distribute the L through, I get 4L minus L squared. So if a rectangle has a perimeter of 8 meters, then the area of that is always going to be 4L minus L squared. So we've expressed the area in terms of its length. That's vital later in the class, because what we're going to want to do is try and see if we can make a connection between some quantity and some other quantity, instead of here where we have a relationship between the area and two things. This equation creates a relationship between the area and one thing, its length. Okay, how about this? A rectangle has an area of 81 square meters, so we still have the same picture. Perimeter, the area of this, they tell us, is 81. Now remember, area is length times width. This was length, this was width. It says express the perimeter as a function of the length. So we want the perimeter as a function of the length. But we know already the perimeter is always twice the length plus twice the width. So what I need to do is find a way to get rid of the W here. Well, coming back here, I have a W in this equation. I know this side's 81. So I know that 81, if I divide both sides by L, I have an equation for W, and I can take that and plug it in here. So my perimeter, is 2L plus 2 times W, but W is 81 over L, which means that my perimeter, oh, I switched colors. Why is it switching colors? Whoa, that's weird. Don't know why that happened. My perimeter now is 2L plus 162 over L. That is the perimeter as a function of the length. So for any rectangle that has an area of 81 square meters, the perimeter of that must be twice the length plus 162 divided by the length. I'm just curious to see how this thing does it. How much they show, I guess I should say. Yeah. All right. Well, they do talk about domain, that the length must be greater than 0. I think that's probably obvious that within this word problem, if you're talking about a rectangle that has a perimeter, that has an area, the length has to be positive. You could not have an area of 81 and have the length be 0 or the length be negative. So, all right, find a formula for the described function. An open rectangular box, volume 7, square base. I think I'm going to bring in this here. Get a new page here. All right, so what we have is an open rectangular box. Open rectangular box. Looks like this. So it's open, meaning that you can see in there, right? It's open in there. So there's no lid on this. It has a square base, which means that if I call this, let's say, length, since the base is square, this is also L. And then let's just call this the height from here to here. Okay? I don't like that. From here to here, that's your height. The length went from here to there. And then that, since it's a square, is also. I know my picture doesn't look like a square base, but I'm putting L there, so that implies that it's square. So I have a rectangular box, open rectangular box, with a volume of 7. Well, the volume of a box is length times width times height. But our length and our width are the same here, right? So my volume is L squared times H. And we're told that that's 7. So 7 equals L squared H. All right, let's just keep that in mind. Now, express the surface area of the box as a function of the length of its base, x. Oh, well, they're calling it x. I'm changing it to L. Sorry, we'll just switch it at the end. So they want us to express the surface area as a function of L. All right, let's go for this. Let's imagine we take this box and let's just look at this front side here. What's the area of that front side? Well, this is H, so that's a little rectangle there. That has an area of LH. But then there's another one on the back. So that's another LH. So far, my surface area is 2 LHs. And then we have an area here on the side, and that's also LH. And then the one on this side is also LH. So I have another 2 LH, which means I have 4 of them. And then I have the bottom of the box, which you can't really see, but there it is down there. So if I'm looking at the box from the top, remember this is L and this is L, that means that this is L squared. So that means I have plus L squared here. So the surface area, now it's not a function of L yet, I'm going to get it there, is 4 LH plus L squared. What I need to do is write this so that all it has in it is L's. So I need to somehow get rid of this H. Well, that's where this comes in. I can solve that equation for H, dividing both sides by L squared. And now taking that and plugging it in up here. So my surface area as a function of L would be 4L times H, which is 7 over L squared, and then plus L squared. And this turns into 28 over L plus L squared. Crazy, I don't know why I did that. That's my surface area in terms of L. Now, to match what the book had, or what they're asking here, we need to change our variable L to X because they were using the X instead of L. So that is our surface area function. Is that it? Oh, the domain. Okay, let me talk about domain. Well, in order for this to be defined, X can't be 0. But that kind of makes sense because this thing had volume, which meant that we had to have some length here to have volume. So our domain would be, in this one, our domain would be L must be greater than 0, and here it would be X is greater than 0. All right, that's the first homework assignment, and I'll get working on the video for the next one. Maybe.